Good morning, everyone. I hope everyone's having a great day. So for our project today, we focus on voltage control, protein insertion for DNA nanopore sequencing, and my name, of course, is Esteban Carrillo.
And my name is Amy Rodriguez.
I'm Daniel Leon.
I'm Amy Mara.
And we were all working with our great mentor, Danielle Guerra, and our PI, Luke Diogarajo.
So what makes DNA sequencing so important? One reason it's important is it allows us to detect certain diseases like cystic fibrosis. Here we have a gene with the marker for the cystic fibrosis, and here we have a gene without the marker. We're able to detect certain markers through DNA sequencing. We focused on improving nanopore sequencing by developing a new sequencing technique that made it, and also that had a device that was more accessible and inexpensive and accurate. Our goal was to work with proteins used during the sequencing. Here we have the following diagram shows how DNA sequencing works. DNA enters the top of the protein, then it makes its way through the protein and across the membrane, which allows us to sequence the DNA.
So before we were able to put the protein inside the membrane, we first had to assemble the apparatus. Right here, we first started off with this Teflon chamber. At the bottom of the Teflon chamber, we added a vacuum grease. After that, we were able to put a sheet of paper which will help us form this polymer membrane. In the middle of this paper, we have an aperture. This aperture is a hole which has a diameter of 50 micrometers. From there, we were able to add chloroform solution which contained chloride and polymer. When the solution was put on top of the aperture, the chloride evaporated and the polymer stayed behind. Here is a picture of the polymer that formed spontaneously in the Teflon chamber. This is a close-up of the polymer membrane. As you see here, the top is the hydrophilic, and the hydrophilic is on top and the bottom. This is attracted to the solvent because of the charge. The hydrophobic in the middle is repelled away from the solvent because it's not attracted to it. So after we had made the polymer membrane, we then added MSPA proteins. This protein is optimal to use because of the way it is shaped, and it reacts with the polymer membrane better than most proteins. After we have added this protein into the polymer membrane, we then apply voltage through the polymer membrane for the polymer to create pocket holes in the polymer membrane so this protein could be inserted in there. The voltage we applied is a voltage ramp. As you see here, it is an increasing linear line. At the bottom we have our time, and we have our voltage as the y-axis. This dotted line represents the minimum of how much the voltage we should apply. Because if we apply too much voltage, then the membrane will rupture, which we don't want, and then we will have to start a whole procedure all over again. On the right graph, we also have time, and our y-axis this time is the current. The current went through the polymer membrane, which tells us in the beginning that it went through, and then it changed the current change, which right here it indicates that the protein was inserted. This picture at the top left shows that the protein was inserted. This protein stays because of the diffusion and the hydrophobic effect.
An important aspect of our research involves collecting and analyzing data. So we do this, one way of doing it is looking at Ohm's Law, which says that current is equal to the voltage divided by resistance. If there's a decrease in resistance, we should see an increase in the current. So if we look at this graph, this is an example of no change in current. After the voltage ramp is applied, we have the same current value. This would indicate that there was no core inserted into the membrane. In this graph, we see a change after the voltage ramp is applied to a higher current. This indicates that there was a protein inserted into the membrane. So if we zoom in to this point here, we can find the moment of core insertion, and we look at where the current, which is the black right here, intersects with the with the blue, which is the voltage. And in this example, we see that the protein was inserted at about 700 millivolts. Compiling multiple sets of similar data, we can try and find an optimal range of voltage ramping to have more probability of protein insertion. So in this graph, we have the y-axis as the number of insertions, and the x-axis is the voltage in millivolts. If you, just by looking at this, we can see that a higher voltage applied will result in a greater probability of protein insertion. So with these experiments, we used MSPA proteins and polymer membranes. Previously, research has been done using lipid membranes, and here we see a difference in the way that they react with the voltage. Whereas in a lipid membrane, you would see a drop-off in a bell curve. Here we see an exponential. This relationship between the voltage ramp and the protein insertion rates is something that the research is looking into to try to figure out why that is the case.
So in summary, we observed that the voltage assisted pore formation. Really what this research was about was to work to improve this innovative device. As of now, at least the technology has only allowed us to get accuracy of about 92%. We would really like to get it somewhere in the 99%, close to 100%. One of the most exciting things about this project was seeing the engineering and the science world come together. Of course, we've seen the science through the chemistry and the biology, but nevertheless, we also seen the engineering world come in with innovative devices we were working for. This really shows that both the engineering and the science world are relatively dependent on one another. For potential applications, if successful, we will be able to read DNA through an all-new and revolutionary electrical-based process. As of now, at least, this research is really only used for scientific research. For example, scientists use this to understand the DNA they're working with. However, if this research continues to expand, we will be able to help with personalized medicine to cure illnesses like cystic fibrosis. And again, this is going to be a great tool because we're working with an all-new and inexpensive and improved method. Last but not least, we'd like to thank our great mentor, Daniel Guerra, our PI, Luke Diogarajan, two great researchers that helped us out along the way by the names of Shahab Mortasai and Justin Buffet, our great coordinators, Maria Napoli, Jens Kuhn, Stephanie Mendez, all our RAs who stuck out for such an intense week. We'd also like to thank the UCSB for hosting this event, the JKC Foundation who helped us have an amazing experience, and the CNSI and the CSEP organizations. Thank you.